Now, our next speaker is Dr. John Richards, who is a very esteemed scientist indeed, and an electrical engineer originally. He's president of the International Society for Digital Earth, so speaking to us from a very elevated position, and was formerly Deputy Vice-Chancellor and Vice President of the Australian National University, amongst many, many other things, which are a list too long to read. So without any further ado, I would love to hear from Dr. John Richards, and would you please make him very welcome to the stage?
Well, thank you very much for that introduction, but I'm going to be talking about something at a much lower level. In fact, I was asked by the organisers, excuse me, to talk about the quantitative dimension, to sort of take it right back to basics and talk about where this all came from and build it around the concept of digital Earth. So what I'm going to do is use this as my model, and I want to tell you how this came about technically rather than philosophically, and then go on from that and say something about the challenges that this is going to pose to analysis. Now, this builds well on what Bill's just said, and a lot of what I'm going to talk about in my presentation here builds very much on the previous speakers today. But when I look at something like Google Earth or digital Earth, I see this sort of digital representation. And what really attracts me, and I'm not a cartographer, I'm an engineer, but what really attracts me is all those cartographic things seem to be changed. You don't have to have map sheets anymore. You simply roam around or rotate or pan across the image. You don't have to have different map scales anymore. You don't have to 1 to 100,000, 1 to 500,000 and so on. You simply zoom in and out. And those servers that Bill talked about take care of all that in the background, thank goodness. We don't need to worry about it. And for a person of my age, what was really neat when Google Earth came along is maps are now no longer permanent things. When I was a kid, if you had a map, you'd put it away and keep it forever because they were so hard to come by. But now they're ephemeral. You know, we have them rolling past the displays on our cars all the time. We print off a Google Earth map to find out where we have to go to get to the convention centre, then throw it away tonight. So we have a very different cartographic view of the world when we have a virtual globe, like a Google Earth or a cesium available to us. And the great thing, of course, it's available over the internet. And then we can build on to that. Then if you have a globe available in digital format, it's like a spherical geographic information system. And you can take all sorts of layers of social, cultural, trade, investment, and so on information, and lay those layers over the globe. And if you looked at the Queensland globe that's being talked about here, there's something like 80 layers of information laid over the top of that digital map base. And that's going to complicate the situation, as you'll see. But the great thing about it being available over the web is it's available to everybody. It trends towards open source. And it doesn't matter whether you're an expert scientist or, as we say, a citizen, the layperson, you can get access to that data and you may be able to do things with it. So what I want to do in my time available is just address two questions. What technically makes digital Earth possible? And what are the challenges that get presented when you come to analyse the data from digital Earth? I'm going to tell you that I think from an engineering perspective, not a computer scientist perspective, it's a convergence of 4 major technologies. And then the challenges, I'll address that quantitative dimension that Tim asked me to look at. And I'm going to lead on to this era of big data, this sort of data volume that we've been told about several times today, and how we're going to cope with that in terms of analysing and making sense of the data available. And I'm going to end up talking to you about the human factor. I'm a great believer in collaborative human intelligence and emulating human intelligence to help us make decisions. Even when we go back 20 years ago, you see the old-fashioned map readers and the old-fashioned photo interpreters putting maps and satellite images and radar pictures on the ground and musing over them one to the other and forming very good inferences about what's on the ground. That's the sort of thing I'm interested in. So if I talk about the convergence of 4 technologies, there are 2 obvious ones. It's telecommunications and computing that came together to give us the internet. But then to me as the engineer, the 2 really significant ones that turned this into digital Earth and made the virtual globe possible is you roll into that navigation technology or positioning technology and Earth imaging. And so you then end up with this construct where you bring those 4 technologies together to create this thing we now call digital Earth or virtual globes or whatever else we want to use. Of course, it's not as simple as 4 technologies. It's underpinned by techniques from geography and GIS, computer science, web browsing and so on. But what it does, and I have to say I don't like this word empowering, but I couldn't think of another word because you know what it means. It means we empower both the professional and the layperson or the citizen alike. So anybody with those four technologies now coming together can do things, as I said before. How do we get to this point? And do we think we'll ever be able to use the virtual globe as a surrogate for reality? That's our objective. And finally, again, how important is the human factor? I put down a timeline here that is probably near to my heart. I was born a bit before that started, but it covers most of my sentient life, if you know what I mean. And I thought, what has happened in telecommunications over that period, and what has happened in computing? Well, if I go back, and I am a communications engineer by training, and look at what I think were the big developments in telecommunications in the last 50 to 60 years, that's what they look like to me. We were looking at cables in the 50s, we were looking at satellites in the 60s, fibre started coming in the late 1970s, and then mobile telephony started poking its head up around that time. And then, of course, everything happened. And I've just put down Wi-Fi and smartphones because they're the two obvious things that define our current utilisation of telecommunications technology. If I overlay computing on the same dates, they're the things that strike me. Now, not many in this room would be in the position I was. I think that when I was doing my PhD, we had one computer in the university, one big mainframe, and all of us did our computing on that one big mainframe. And then, of course, in the ensuing decades, we went through mini computers and workstations and now PCs and Macs. And you'll see that I put smartphones there as well, because I can't quite work out in my mind whether a smartphone is a computer or a telecommunications device. It's actually a combination of both, of course. But what happened then is a range of services were developed, starting with ARPANET, of course, which was the generator of the whole thing, moving through internet, and then to email, and then to the internet itself. And then, as we've heard, Borna's work on the World Wide Web. And so together we now tend to group all that, and we don't talk about telecommunications or computing anymore. We tend to talk about ICT, because it's all been brought together by those applications. A couple of years ago, somebody said something which is just stuck in my mind, and I'll put it up here. Again, it's an age-related thing. The kids of today have never known the world without the internet. The internet is so much a part of their life, whereas I can remember a time when we didn't have television. And so this technology has just developed rapidly. And of course, the internet is great because it puts people in touch with people, and it puts people in touch with data, and people in touch with with knowledge. And so you have this open communication prospect built up through the internet as a result of the convergence of telecommunications and computing technologies. So that's the first two of the technologies. Now let me talk about navigation and Earth imaging, just briefly, just to sort of create the historical perspective. We've always wanted to know where we are, and some of you will be quite aware of the problems in the 16th and 17th centuries with trying to determine longitude and the need to develop precise clocks and so on. And indeed, there are all sorts of apocryphal stories that we've read about with Captain Cook and others and Harrison with his clocks to make navigation possible in those times. And then, of course, those problems were solved, and so we ended up with systems around about the mid-1940s to 1950s based upon global transmission of HF and very low frequency signals around the Earth so that ships and aircraft and so on could position themselves. They were the surface-based systems. Now, surface-based systems are fine, but not very good if you want to overlay them into the internet to make up a digital Earth. So you look at a satellite-based system. The first satellite system was transit, and a number of you will know how that operates. It's a Doppler-based and a Doppler rate type system, but again, not very convenient if you want to try and overlay positioning information onto a virtual globe in an internet type environment. It wasn't until the global navigation satellite systems like GPS came along that we suddenly had a system which was fast, it was moderately reliable, it was simple and accurate, and at the right sort of scale and the right sort of timeliness that you can actually integrate it into the virtual globe type format. Before that, it just wouldn't have been possible. And what about the satellite side? Well, a number of us in this room, not many, will remember the early days of satellite imaging of the Earth, and it all started with Landsat back in 1972, and the imagery was typical of the one you see on the right-hand side here. In fact, we saw that one again this morning. Again, you wouldn't have used that principally as your data source if you were developing a Google Earth, but it is used, of course. But what is better, is the fact that you're not dependent on one satellite now. We have many tens of satellites. There has been an explosion of data availability through satellites in the ensuing decades since the first of the Landsat satellites. Not only the numbers of satellites, but of course the data from them. And what's happening now, of course, is there's a trend towards satellite clusters. Hundreds, perhaps to thousands of smaller satellites that will take the place of larger satellites in helping image the Earth. Now, what's more important, I think, is not so much the increasing number of platforms, but the quality of the data. And this slide here shows the two extremes. On the left-hand side is one of the first images ever taken of the Earth from space by a TIROS satellite in 1960. On the top right-hand side, you've got a typical high-resolution satellite image which shows on Google Earth. And you immediately see that the left-hand side is not too good if you want to manage urban resources, for example. The top one is fabulous because it shows you even shadows of the tower, the flagpole over Parliament House. And so that increase in data fidelity, increase in resolution, again, just matches perfectly the concept of what we need for digital Earth. And so it's those four technologies, in my feeling, that come together to make this virtual globe type of product something which is meaningful and hopefully, as it says at the bottom of the slide there, with time, may be able to be a surrogate for reality. Now, you may have different views on whether that's good or bad, but there are many people involved in the digital Earth community who would like to set up the virtual globe as a surrogate for reality in legal transactions and commercial transactions, as I've suggested there, and also in science. It's an easier way to do things often than going through the real system. Let's suppose we've got to that stage. The issue I want to talk about now for the rest of my time is how do you analyse the data, or how do you utilise the data? And I've drawn what I've called there a decision support spectrum, where all decision-making type of managers, we all want support from some particular data set in making decisions about the domains over which we have responsibility. The majority of the time, we're working down that left-hand end. The majority of the time, we're working with manual interpretation. And indeed, all these wonderful rendering and presentation techniques that we've talked about are aimed at making it easier for the resource manager as a person to look at the data and extract the information in which they're interested. But the data's increasing in volume and complexity. And I think there's a need to try to move up towards the right-hand end to have machine-assisted interpretation, perhaps not fully machine-interpreted data, but to move up a bit so that we can take benefit from machines helping us to understand what we're looking at in the data. And so that's the part I now want to talk about and try to convince you that artificial intelligence emulating the human being might be a way to handle the data volumes we're looking at. Now, to do that, let me tell you that I'll use satellite imagery as an example. There are two very general approaches we have used over the years to analyse satellite data. Excuse me. And the left-hand one is not unlike what we do when we look at the sorts of materials we've looked at in the previous talks today. We call it photo interpretation in satellite data, and it depends upon good visualisation and good rendering of the data. But when you want machines involved, you have to move into what we call, well, a number of names. I've called it classification here, a semi-automated technique where you can train a computer algorithm, and this is really simple stuff to do. You can train a computer algorithm to recognise parts of an image and give those parts of the images labels. So in that particular case, we've turned the image recorded by a satellite into a map of bushfire signatures in the northern suburbs of Sydney. Now, we've been doing that since the late 1970s with no difficulty whatsoever. But the challenge is going to be what happens with newer data types or increased data types. So let me do a quick example with you. The amount of data that's recorded by a satellite sensor is defined by those parameters illustrated on the slide. It's the number of distinct different wave bands that are being recorded by the satellite sensor. It's the number of pixels within a frame that are being recorded, just like the megapixels on your camera. And it's the range of bright to or black to white for each of those pixels, the so-called dynamic range. When you bring all of those factors together, they define how much data is being recorded and transmitted back to Earth by a satellite. I've used 3 examples here to show you how this data volume is changing. The very first of the operational sensors, the Landsat multispectral scanner, it records just a tad under 20 megabytes of data. We jump ahead about 20 years to the Landsat Thematic Mapper, it's an order of magnitude greater. Excuse me. If we go to satellite from last year, WorldView, one of the most recent ones, WorldView 3, with resolutions around 1 or 2 metres on the ground, we're recording there 1,400 megabytes of data. Now, actually, that doesn't mean very much, but it means more if we try to work out how much data is being acquired over the same region on the Earth's surface. For example, a strip about the size of Australia. So if you look at a strip over the size of Australia, you're looking at 250 megabytes of recorded data with Landsat MSS, looking at, haven't got my glasses on, but looks like 3,200 megabytes of data for the TM, and some enormous number, 260-something megabytes of data, gigabytes of data, for the Landsat, the WorldView 3 satellite. So you can see the problem. That we know this is a problem. We just know that data everywhere is expanding, and we've been told about that again in previous talks. So the question is, will the sorts of machine learning, simple statistical and other types of techniques be adequate when we're trying to analyse data of this type into the future? Now, it's exacerbated when you think that over this virtual Earth, this digital Earth, we can lay cultural data, social data, spatial data, satellite interpretations, and so on. And so the question is, how do we cope with such a large and complex data set? Well, when I sit down and think about it, I think there are 3 approaches that I would look at. First is build bigger computers, build more powerful machines, and that's not unreasonable, because more powerful machines can, as a second dot point there says, generate products we can put back into our digital Earth for users to put to application. But what you don't want to do is take this material, take this technology away from the reach of the citizen with a desktop machine. And so the first point there is particularly important to me. Supercomputers might be good, but you don't want to disempower the citizen. So the next approach you might look at is being more efficient in your algorithms. And people are looking at this. Can we make algorithms that scale well? When the data volume scales, do the algorithms maintain their expansion? Can they still work as quickly? And we still have a long way to go to handle what is generally called the multi-source problem. How can you form an analysis between radar, optical, LiDAR data, for example, and perhaps soil maps? People can do it really easily, well, moderately easily. Machines have a problem still with doing that. But the third approach, and the one I want to have people explore, and I'm not a computer scientist, so I'm not capable of doing this myself, but is to emulate human reasoning, to use artificial intelligence. Because as I say there, we're all good at complex reasoning, and we're good at reasoning over mixed data types. We have some problems, which I'll highlight in a moment. But just to highlight, or to use a very simplistic example to demonstrate why I think humans are good, take visual information processing. Now, this figure of this optical resolution of the human eye of 0.0128 degrees is what I got from somewhere. And if you apply that to a field of view, which is, say, 90 degrees by 90 degrees, which is more limited than most people's peripheral vision, you get about 500 million pixels of data, at least in principle. I'll qualify that in a moment. Humans can distinguish about 1 million colours, and to code 1 million colours, you need 3 bytes per pixel per colour primary. Humans can cope with scenes which change about 20 times a second. So if you bring all of that together, it means that in a typical scene, we could be looking at 30 gigabytes a second of data coming into our optical system. The reason we don't is because we tend to stare. we don't take in that full visual field at the same time, we stare. So we might take in, say, 10% of it or less, but that still means we're processing about 10 terabytes of data per day in a 10-hour day as human beings. And we're making sense of it. For example, if we saw a fire, something as simple as that, and we need to tell the authorities, it might take us a second or so to assimilate the fact that we're looking at a fire. So we're taking in, I've said there, 0.3 of a gigabit of data. We want to pass a message to the authorities, say 200 words, that's about 10 kilobytes. We've compressed that information in our interpretation by about 30,000 times. And we've been able to use all those skills in our visual interpretation system to cope with that huge data volume. And why can't we do that by machine? Now, there are some reasons why one's good and one's not good. We as humans are very good at making complex high-level decisions. We're good at spatial information processing as well. We can talk about relationships easily and sizes and shapes and textures. Machines have problems there. The problem we have as humans is we get tired. We can't do it as repetitively as well as a computer can. Neither can we assimilate the data volume, the data complexity that a computer can. And what I'm leading up to here is a bit on the bottom of that slide, which says, wouldn't we get the best of both worlds if we could emulate in a machine human thinking and take all the advantage that machines give us as well, like not getting tired and doing things accurately? Now, how do we do that? Well, I think there are two approaches. One is simply to use artificial intelligence, excuse me, and computer scientists have been developing expert systems for 20-odd years now. They need a fair degree of sophistication to do what I'm talking about, but why can't we do that to help us solve this big data problem in the digital Earth environment? Or why don't we learn from insects? Why don't we engage swarm intelligence? Why don't we try to build some form of intelligence over numbers of people, numbers of citizens, making decisions in a way that insects and bees and birds and fish and that do. So let me wind it up by drawing it all in a diagram. So to me, this is where I start. We've got this wonderful thing called the internet, which serves everybody. The internet makes available the assets in a digital Earth, and we want to use artificial intelligence as much as we can in order to process that data to make the data available to decision makers. But on the other hand, we don't want to make it too complicated if all of those citizens out there can work together, because citizens joined to the internet can talk to each other and can talk to the data. And why don't we see if we can somehow emulate group intelligence by using hundreds of citizens to help us crowdsource and understand what we're looking at? And probably haven't got time now, but I have another little set of slides I might show later on in discussion that might just illustrate this point again. This is a ring in this bit here, but I think what we have never succeeded in doing in this country or internationally is building knowledge brokers, people who can actually sit between the client and the data and the internet, take the client's requirements and turn those requirements into analytical requirements, contract analysts and build the result required by the client. That's not quite in the theme of what I'm talking about here, but I think we need to do that in the future as well. The important thing, though, is that the internet facilitates those. It facilitates linkages and facilitates networks. It puts citizens in touch with each other, citizens and experts in touch, and citizens and experts in touch with data and knowledge in a truly open source way, if we could get to that. So 3 take-home messages. The internet and digital Earth grow because of human ingenuity. It's simply the ability of the human to be ambitious, to be intelligent, to be inquisitive, to build systems like the internet and use them in ways that were never intended. We have domain-specific globes out there now. I've listed some there. And those domain-specific globes are verging towards what I've said before of surrogates for reality. Michael Haynes here at some stage may talk about Vanzi, his approach to using a virtual globe as a surrogate in property transactions. But to me, with the increasing data volumes and the complexity of the data, the real challenge for us is, can we do it better? And can we do it better by emulating what humans do? Thank you.